Hello everyone, my name is Amir Ahari. I'm a Google Earth Engine expert. Welcome to this video. Today I'm gonna show you how we can calculate the area of a snow cover in the Google Earth Engine platform using JavaScript. Let's go to the Earth Engine code editor environment. So in the first step, we need to identify region of the interest. You can draw region of the interest by drawing tools available here. For example, I prefer to use draw a rectangle to select a region in my own country for the snow cover area calculation. Remember that you need to select an area that is covered by the cloud, that is covered by the snow for a period of time. So, for example, in my own country, a snow cover mostly happened, or a snowfall mostly occurred in the north and northwestern of my own country. For example, I select a region in this area that is most of the time during winter or under a snowfall. So then, to have focus on the study area, use map.center-object at the first of your code. Map.center-object enables you to have focus on your study area, that is geometry here. Whenever the code is run, you can see that we can have focus on the study area, just like that. In the next step, you need to call a snow cover product through the search places and dataset. Go to Browse Data Catalog. In the Google Earth Engine Data Catalog, you can browse your desired data through the available tags here. So just write snow. As you can see, for now, 11 datasets are available. So if you go there, you can see and have access to variety of snow cover products available here, and some of them provided a snow cover data with a few hundred meter spatial resolution, such as Modi's product, and some of them providing a snow cover product or a snow cover information with the kilometers for example, in 5 kilometers, in 10 kilometers, and 20 kilometers. It depends on your goal, which one of these products is suitable for you. But if you want to have a local study for a snow cover, I highly suggest you to use Modi's snow cover product. Is available with the daily temporal frequency here and in Terra and Aqua satellite. As you know, Terra satellite's data available since 2001 and Aqua available since 2003. So, for example, here I'm gonna use Terra snow cover here. It's available since 2000 exactly, and a image collection snippet is here. The spatial resolution is 500 meter, and also we have different bands here available. One of them is NDSI snow cover. Here NDSI means normalized difference snow cover, an applicable index to show or highlight cloud cover using the satellite imageries. As you can see here, a snow cover calculated based on the NDSI and ranges from 0 to 100, and also you can see that and also the NDSI snow cover showing the amount of snow cover in each pixels. For example, when one pixel labeled as 100, meaning that of all the pixels or all the regions covered by the pixels covered by the snow cover. For example, if the snow cover is 50, means that the only 50% of your, or 50 or a half part of your study area covered by the snow cover. So it is very helpful index to interpret the snow cover result from that's extracted or calculated from the NDSI. So here I want to show you how we can calculate the snow cover here, how we can get area of snow cover for different dates. So just you should call this product in the code. To call this product in the code, first copy the full name from here and paste it into the search places and dataset. You can see it exactly here and import it as an image collection. Make a new variable. The new variable is modis snow cover or modis NDSI equals to image collection. We are assigning image collection to the modis product. So for the next step, we need to set a start date and end date. Dot filter. So we need dot filter date. Filter date is a filter that narrows down the image collection to a specific period of time. I'm gonna making two variables here. One of them is time start and the other one is time end. Through the time start and time end, I'm able to set a start date and end date. For example, I want to calculate the snow cover area since 2010 to 2020. A start date or time start could be 2010 and time end equals to 2020. For 10 years, we want to get the area of a snow cover for the selected region. So, and then as we are working with the coarse spatial resolution and also it has no framing structure such as Sentinel-2 and Landsat images, no need to set a filter bound here. So in the next step, get a print from modis variable to see that how many image collections available during this period. More than 3,000 images available because this is the daily data, and for each year at least 365 images available, and during 10 years you can see that provided more than 3,000 images. So for the next step, we need to set a threshold to actually separate the snow cover pixels from non-snow cover pixels. For example, here I want them for 1 year. Imagine that for only 2010, from 2010 to 2011, just I want to get an average image from the snow cover product and calculate the area for 1 year or one average image, and then I will show you how we can extend that code from a single image to a time series. So in this step, make a new variable, for example, variable NDSI min equals to get modis data for 2010 and then get the median value in each pixel to prepare one single image, because in the first step I want to show you how we can calculate the area for one single image, and after then I will show you how we can extend it for the time series. So here I'm using map.addLayer to visualize NDSI average or NDSI means. No need to visualization parameter to add some parameters related to the visualization part, and also it is NDSI for 2010, and to avoid automatic loading image I'm using false at the end. So run the code, and after a few moments the image is available under layers option. So check it on and wait until the image appeared here. But here we need to select one specific band that we are working, because if you go to the data descriptions through the bands, you can see that the only bands we need to work is the NDSI snow cover, and also no need to any scale factor. So before visualization, I had to select the desired band such as NDSI and then get its median. So And also to have focus on our study area, I want to clip it based on the geometry already defined here. So again, check it on after code running again. So as you can see here you can see that. So as you can see, image is loading, and we can increase the contrast by stretching methods. The values ranges from 7 to 63, meaning that some of the pixels, some of the NDSI value in some pixels, lower NDSI values such as 7, showing that we don't have so much snow cover in such pixels, but 63 showing that too much snow cover in some pixels in contrast. One big uncertainty in the satellite data in the NDSI product is the water. And also before calculate the area of the area of a snow cover, we need to mask water area or the water pixels from the calculations to increase the efficiency of computations, because we want to only get the area of snow cover and we don't need to the area of water area actually. So to do this, you can use some of the available products, some of the available snow cover, some of the available land cover products to make a mask for the water area and then remove the water from NDSI product. As you know, Modis land cover product is available, and through the search places and dataset, I want to call Modis land cover image, and then using the class water, I want to remove the water areas from the snow cover product to have only access to the non-water pixels. So to do this, through the search places and dataset, write Modis land cover. In the previous tutorial in my YouTube page, I showed you how we can use Modis land cover product for the area calculation or something like that. As you can see, Modis land cover product available with 500 meter spatial resolution. It is annually, and also as image collection number 2 is available here. So LC meaning land cover product, it is available since 2001, and I want to get a mode of each class for the study area to prepare a single land cover map and then use it for make a mask for the water area. So LC equals to image collection number 2, Modis land cover product, and then as this product including different standards for the land cover, as you can see in the bands LC type number 1, 2, and 3, and also it is available based on different standards. It should be noted that mostly people use LC type 1, and typically we use this band or this standard for the land cover product because it has enough diversity for the classes, and also we can have a good interpretation for diversity in our study area. So, and dot select LC type number 1 selected, and to get a mode of each class to prepare a single land cover map, I want to select or keep only those classes that that happened or occurred yearly, and most of the time they are available in our region. Actually, I want to keep those of classes that are more stable than others. So for each pixels, we get a mode here, and then we need to know that which value in LC type number 1 showing water area. To do this, go to the band's description here, and there is a class table for each standard, And as you can see, class number 17 showing the water bodies in our study area. So, and then we can select the water bodies, make a new variable, WB, meaning water body here. From land cover, only we want to get the water body, those values equals to 17, and then if I use map.addLayer for the water body that is clipped based on the region of the interest, you will see that water body here. As you can see, only we have a water body here, and also, but for a mask layer I need to set 0 for the waters and set 1 for the non-water pixels. To do this, after equal, if you use dot not, you can do it very well, and also you can set value 0 for the pixels with number 17. As you can see here, now we have a mask layer in which water areas or water pixels including 0 and the rest of pixels showing a number 1 value. So now I can apply this mask layer on NDSI average that is already calculated. So to do this, for example, I copy NDSI.mean with map.addLayer after a water body. So, and then after getting median, I want to use that update mask, as you can see, update mask by water body to remove the water bodies from the available from the average image. Run the code again, and now we can have access to NDSI 2010 with lower with the no water content actually. And as you can see, the water completely removed from the pixels. And here I want to get an average. Unfortunately, I think getting the average for 1 year is not appropriate way for the visualization, because only for a few days or only for a small period of time we have we have a snow cover. For example, in order to have access to all snow covers in our study area for a sample image, we can get the maximum value. So, so here, instead of getting median, I want to get max to show the maximum snow cover for our study area. So now works better. You can see the distribution, the spatial distribution of the snow cover in our region. This is the maximum snow covers distributed in our study area, and here you can see that these are highlands, mountainous regions that most of the time covered by the snow, and we can have a better visualization by 90% contrast. Yes, now works better. That was the problem. Actually, the snow cover only covered our area for a small period of time, and when we get median or an average for a whole year, definitely we can't show, and also none of the snow covers highlighted very well in such situation. So now imagine that I want to calculate the area of a snow cover in this region for the selected study area. For in the previous tutorials in my YouTube channel, I showed you how we can get the area of different phenomena, different land covers and NDVI croplands or something like that. I'm gonna use the same scenario here to show you that the script is same, and the only thing changes here is the input bands, input collections, and the thresholds that we set. If you have information about the threshold, if you have information about the products, then you can use the same code for the variety of products. And that's the way that you can learn how to deal and how to work with the Earth engine. My goal in this tutorial, in my YouTube page, is that help you to learn the Google Earth engine, not only pick a code to do your project temporary and pass the challenge you are facing. Yeah, actually, I want to show you how you can learn it. And learning is very, very important, because when you learn something in future, definitely you can develop it. So now I want to make a threshold to get the area of a snow cover. As you know, the range of NDSI product varies from 0 to 100. I want to select those of pixels including a snow cover above 10 and between 10 and 100 and get their areas, for example here. So the threshold THR equals to, from NDSI, this is not min anymore, this is max actually. I want to solve it. NDSI max. So I want to select first those of pixels including cloud cover, those of pixels in the NDSI that's having values greater than 10. .gt 10. For example, I want to select those of pixels that the snow cover in them greater than 10%, for example. So, and then I want to, and also after we make a threshold through the map.add layer, you can see the threshold image here very quickly. And this is the threshold for values 10, and then use the false to avoid automatic visualization. This is NDSI max, and in the threshold image, now you can see that all the pixels having value greater than 10 equals to 1, and the rest of pixels equals to 0. I want to clip it based on the region of the interest, and so in order to avoid overestimations in the computations, I want to increase the rate of the snow cover per pixels. For example, I want to set it to 50 to select those of pixels, at least half of them covered by the snow. So I think that is helping us to get more realistic estimations about the snow cover, because you can use any threshold to get a snow cover area, and also it's very important to set a threshold that gives you a realistic result without any huge overestimation or huge underestimations. So now this is threshold for 50. I think now it's more realistic for the maximum image that I'm working. So, and also here we have a threshold for 50. So in the next part, I want to show you how we can get the area of each pixel highlighted with white color. So make a new mask. First, we need to make a mask to remove the 0 values from the images. So here we have a mask, THR here, we have threshold image that update mask. Update mask is a function helping you to remove 0 values and keep the snowy pixels. So I want to visualize it again here through the mask dot clip geometry, And here we have mask of pixels with 50% or above cloud cover, snow cover. Sorry if I say cloud or something like that, because most of the time I'm dealing with cloud in the satellite data. So, and so run the code again, and now you can see that the zero value removed and the only snowy pixels remained here. So now we want to get the value of area of each pixels instead of value number one. For example, by the inspector, if you select on each pixel, you can see that in the mask image the snowy pixels showing by value number one, but I want to get the area of each pixels instead of the number one. So to do this, make a new variable such as area equals to get mask image dot multiply earth engine dot image dot pixel area. The pixel area is a function that calculates the area of each pixels. So in order to convert it, and also now I want to convert the pixel area values from a square meter to a square kilometer by a division to, for example, 1 million. This is a constant to convert the pixels from the area from a square meter to a square kilometer. So we can visualize it again. Nothing changed visually, but we have the value of area of each pixel instead. So the area, the mask replaced by area, and here we will have area, and through the visualization, as I mentioned, nothing will be changed, the same image, but uh, this time when I click on one pixel instead of value number one, we will have the area of that pixels in a square kilometer. That's very important thing. For the next step, I want to get the sum of the area values estimated for each pixels, because that would be the area of snowy pixels at the end. So make a new variable. So this time snow area for the region equals to get the area image, the image including the area of each pixel for the snowy pixels, and then through the reduce region we will be able to get the sum of these area for our study area for the identified region. The reducer could be Earth engine, or should be Earth engine dot reducer dot sum, and then the geometry, the region of the interest equals to geometry. Sorry, my language, keyboard language changed. And scale should be equals to the scale of image. The scale of image or spatial resolution of this image is 500 meter, and also scale could be 500. And after scale we will have max pixels, the maximum pixels that load for the computations 1E13, and that's enough for the getting the area values. So in order to get the value as a number, we need to use that values that get the values from the first item, and Earth engine dot number should be added to consider it as a value. And now I print the snow area, the area of snowy snow cover area here should be, for example, snow area equals to snow area. So in the right panel, after a few moments, a snow cover area based on a square kilometer is available. The number is under computing. Larger area, a longer time for computing, smaller area, shorter time for computing. That's important. So if you had any question or any problem regarding this tutorial, you can put your comments uh, uh, under this video in my YouTube channel, and also I have shared the tutorial code for you to compare your own code with my code, and that will help you to find your errors during the scripting techniques. But feel free to reach me out if you had further questions. So because the area is a little big, calculation for the area is a little time consuming. And sometimes a few seconds and sometimes 1 minute maybe take to return the results. It depends on your study area, it depends on number of the pixels involving during the computations, and also the internet speeds and variety of things and criteria affect on the speed of processing in the Earth engine. For example, here, after a few seconds, you can see that this is the value. This is the value showing the area of maximum snow cover for my region of the interest. And also now, I want to show you in the next step how we can use the same code and same step for the time series analysis, how we can do it for example, for 1 year, or for 10 years. So before, the modest image collection using NDSI snow cover and time start and time end imported into the code, and now I want to make a new variable and a new function to use these steps in the body of a function, and to repeat this process for each available images. For example, for 1 year, we have 365 NDSI image. For each date, I want to select those of pixels in which the snow cover value is greater than, for example, 20 or 30, and then get the sum of the area and plot it for me to show that how much cloud cover changes in this area. So now I make a new variable, NDSI. This is NDSI equals to get modest images for 1 year, and then throw a map. I want to make a loop here. In this loop, I defining a function that functions helping me to do this calculation for each available images. Each input image in this function considering as an IMG, and then through the first variable that is threshold or NDSI threshold, I can select from each input image those of pixels in which value is greater than, for example, 20. So here and 20, and then for the next variable, I want to mask the zero values from the threshold image as NDSI mask equals to get NDSI threshold dot update mask NDSI threshold again. So to get the NDSI area, you can see that the same code I'm using here just inside a body of a function and using a map. I'm doing this for all available images under modest image collection. So NDSI area gets NDSI mask, and then dot multiply Earth engine dot image dot pixel area. Now we get the area of a snowy pixels dot pixel area, and then to convert it from a square meter to a square kilometer, uh, uh, we have a division to 1 million. So finally, return NDSI area with all property of input images, specifically system time start and system time end. And finally, in the next part, to show the sum of the NDSI value, the sum of the area of snowy pixels for 1 year, you can use a chart. User interface dot chart dot image dot series. So couple of arguments available here. Instead of replace image collection by NDSI image, instead of the region, we have our location as geometry, and reducer here is important. Here, for each date, now we have the area of snowy pixels. So to get the sum of the area of snowy pixels, we need to get reducer, we need to use Earth Engine.reducer dot sum, just like that. And instead of a scale, we need to have 500 meter because the spatial resolution is 500 meter. And instead of X property, we will have system time start that's showing the time spans for our study. So run your code, and now chart is under generating. After a few moments, you can see the chart or daily chart of snow cover changes in your study area since for 2010 for only 1 year. You can use the same code to extend your period of time. For example, as you can see that this is a final plot that's showing that we only have a snow cover for the wet times. For example, for the winter, we from the January to April, we have some anomalies, or we have some snow cover, we have some snow in our region, and also in the December again started. And also this is a very valuable code that helping you to see that when the snow cover is melting and when snow cover creating, and also it's very helpful to interpret the snow cover regarding to the temperature or something like that. And these are the area of snow cover based on a square kilometer, and you can have access to the Excel file through the download CSV. It's very important things. And as I mentioned earlier, you can increase the time span to, for example, 10 years or even more. And here, for example, yes, for example, I increase it to 5 years because this is daily, thousands of images, maybe take a little time, and also it is not suitable for this kind of tutorial. You can try it by your own. For example, I increase it for 5 years. 5 years, more than 1,000 snow cover product is available. More times needed to process the results, and you need to be patient when you are working for a longer period of time, and also more detailed temporal frequency data. It's take consuming to do computations for a relative large area, and also longer extent and higher frequency. And so until a chart is generated, I can show you how you can get the export from the images, because somebody asking me questions that we don't want to get the area or something like that, just we want to get export from the images. And also if you want to get the export and also the result is also ready, you can see the variation of the snow cover. And also I'm using the extra time to show you how to get export from the NDSI area or any other images you want to work with a snow cover. So export that image that to drive, helping you to get export from all images you need. For example, the image I want to get export is the NDSI image, but I want to get export for a period of time. Through the dot filter date, I want to get export only for example, 2011, for example, and maybe you want to get these images only for winter time. For example, only for January. This is very helpful technique. In Earth Engine, we have calendar range, Earth Engine calendar range, helping you to filter your data only for a specific period, a specific month, a specific date, a specific day of week or something like that. For example, I want to get all the images for these for the January, the first month of year, and here the start month and end month is 1, and finally I want to stack them into a single file dot two bands, helping us to make a stack, and then through dot clip I want to crop the final image based on the region, and the description is the name of the output. It is, for example, modis NDSI, whatever you want you can set, and the scale should be 500 because the spatial resolution is, and the region should be geometry. These are necessary things that you should consider, and if you want to have a georeference output with the WGS 84, you need to write this code. Yes, 4326 EPSG, and so that's it. No more codes need, and also if you run the code you can get export only for the January of, for example, 2011. So go to the task and click on run. After a few minutes, once the storing process or saving process ends, it's turned to the blue color, and you can download it from here from the Google Drive. Thank you for watching me. I hope you like it as much as we do.